The next group of functions we will look at in Chapter 4 will be logarithmic functions in Section 4.2. Let's start with the definition of logarithmic functions. We need to understand the relationship between exponential functions and logarithmic functions. There's one basic relationship for these concepts that you can really focus on to help understand that relationship. And it is this, that any numerical value can be expressed as the combination of a base raised to an exponent power. So I'll refer to this as the base to some exponent equals a numerical value. So, although a simple example, if my base is 2 and I raise it to an exponent 3, I can represent the number 8 in that way. So remember, some base raised to some exponent can equal any numerical value. And we can write this relationship as this: our base b to some exponent y will yield us some numerical value x. So b to the y equals x. Base to an exponent equals a value. Now, remember, our exponential function, f of x equals y, is the base b raised to some value x. Now, that is a one-to-one function. Remember, that language means that it does have an inverse function. But what is that inverse function? Well, if we use our switch and solve strategy from section 2.7, we would take this equation here, switch x and y, and then solve for y. But notice this looks a bit different than what we worked on in section 2.7. How do we solve for y? Well, that's going to lead us to the logarithmic function. F of x is the log of some base b of some value x. And x has to be a value strictly greater than 0, b has to be greater than 0, and not equal to 1. Now, how is our exponential function and our logarithmic function related? Well, remember I said we really want to focus on this relationship. A base to an exponent equals a value. And in this form, we would write b to the y equals x. So, if we have that relationship, some numerical value is a base b to some exponent y, well, what does the logarithmic function do? Well, what the logarithmic function will do is, for a specified base b and a given numerical value x, it will return this exponent y. And that exponent y is a numerical value that will bridge a specified base b and a numerical value x. So again, notice you have the base, you have the value, the logarithmic function returns the exponent that will join those two values. So this is the key relationship to understand when you start learning about logarithmic functions. For a specified base b, the logarithmic function calculates that exponent y to create a given numerical value x. And we can switch between two forms. We can switch between an exponential form of this relationship between these three pieces and then a logarithmic form of this relationship between these three pieces. These three pieces will all be in each form. In logarithmic form, the exponent y is log to the base b of the value x. And then in exponential form, here's our base to the exponent equals the value relationship we started with in the chapter. In example 1, on page 479 of your textbook, we're asked to convert from logarithmic form to exponential form. Remember, you'll always have three pieces: a base, an exponent, and a value. So just carefully identify those pieces and then write the logarithmic form and exponential form. So here, the 2 is our exponent. 5, which will always be in subscript, is the base with your log function. And then x is the value. So for this particular example, our base is 5, our exponent is 2, and the value is x. In part B, the exponent is 3, the base is b, and the value is 64. So again, we want to go to this exponential form. So the base is b, the exponent is 3, and the value is 64. In part C, our base is 3, our exponent is y, and our value is 7. In example 2 on page 480 of your textbook, now we're given expressions in exponential form, and now we need to convert it to logarithmic form. Again, we'll still have the same three pieces, a base, an exponent, to a value. So in this first problem, the exponent is 2. That's the result of our logarithmic function. And then the base is 12. I'll write that in subscript. And then the value is x. In part B, our exponent is 3. And that will be log to the base b. And again, I'll write that in subscript. And here, the value is 8. And then in part C, the exponent is y, and it will be log to the base e, and the value is 9. So in any of these problems, whether you're converting from logarithmic to exponential form or exponential to logarithmic form, carefully identify your three pieces when you put it in the appropriate form. Logarithmic expressions can be evaluated without a calculator if the numbers are certain values that can be evaluated manually. In example 3 on page 480, we'll evaluate logarithmic expressions, but again, we're going to utilize that basic relationship, a base to an exponent equals a value, to evaluate these expressions. In part A, our base is 2, and the logarithm is going to return some exponent y that will connect with the value of 16. And so in this case, y would be 4. 2 to the 4th is 16. In part B, again, we'll identify the base. And the result of the logarithmic expression will be this exponent y that we're looking for. And that is going to equal some value 1 over 49. Now, just remember, 1 over 49 is 1 over 7 squared, which is also 7 to the minus 2 power. So in this case, y will equal minus 2. In part C, the base is 25. We're looking for some exponent y that will make that value 5. In this case, using our rational exponents, that is going to be 1/2, right? Anything to the 1/2 power is the same as the square root, so the square root of 25 would be 5. And then in part D, our base is 2. We're looking for some exponent y that will give us the 5th root of 2. But remember your rational exponents. That can be written as 2 to the 1/5 power. And now our answer is y is 1/5. So you can get fractional answers when you evaluate logarithmic expressions. Just watch your exponents carefully. The next topic we'll look at in section 4.2 is on logarithmic properties, and there are two groups. The first group is properties involving 1. If we think of our base to an exponent equals a value relationship, it's easier to understand these properties. So, b raised to some exponent equals b. Well, that exponent would have to be 1. So this is our first property involving 1. And then b to what exponent would give me just the value of 1? Well, b to the 0 would give us 1. And so that's the second property. And I've included a couple examples from example 4 on those properties for you. Now in the inverse properties, again, we'll use that relationship to look at them. So b to what exponent would give me b to the x? Well, that exponent would have to be x, correct? Base to the exponent equals the value b to the x. And then b to the log base b of x equals x. You could think of these inverses as undoing the actions of another, but this whole expression, log to base b of x, returns the value b to y equals x. So of course, base b raised to that exponent y must also equal x. And again, I've included two examples from example 5 to illustrate those properties. Now, do pencil problems 1, 2, 3a, 3b, and 4. The next topic in section 4.2 is graphing logarithmic functions. Remember, exponential and logarithmic functions are inverses of each other. So while you can calculate coordinates for a logarithmic function directly, it can be easier to just calculate the exponential function coordinates and then just switch those x and y values to obtain the logarithmic function coordinates. Example 6 on page 482 will help illustrate this concept. We're asked to graph f of x equals 2 to the x and g of x equals log to the base 2 of x, which are inverses of each other. So where we can start is coming up with our points for f of x. We can pick those 5x values that we use. This will be 1/4, 1/2, 1, 2, and 4. Now that we have the coordinate points for f of x equals 2 to the x, we really have the coordinate points for g of x equals log to the base 2 of x, because they are inverses. So as we did in section 2.7, we'll just reverse or switch the x and y values. Very often when graphing a logarithmic function, it's much easier to generate the table of coordinates for the exponential function and just switch them than try to develop them directly. When we graph f of x and g of x in the same coordinate system, again, because they're inverses of each other, we get this symmetry around the line y equals x. And focusing on the graph of the logarithmic function, we'll see that it does approach minus infinity as it goes closer to 0. So realize for logarithmic functions, there is a vertical asymptote at x equals 0 if it hasn't been transformed or shifted. Similarly, remember for exponential functions, we had a horizontal asymptote at y equals 0. But now for logarithmic functions, there is a vertical asymptote at x equals 0. When we look at the domain and range of these functions, remember for our exponential function, domain is all real numbers, and range is 0 to infinity because of its horizontal asymptote at y equals 0. Now for the logarithmic function, of course, these values have switched. Its domain is 0 to infinity due to the vertical asymptote here at x equals 0, but now its range is all real numbers. When we work on transformations of logarithmic functions, like we did in section 4.1 with exponential functions, we will only consider horizontal and vertical shifts. We'll continue to use the tabular method, but as I showed in the example above, it can be much faster to obtain the coordinate points for a logarithmic function by first finding the coordinates for its related exponential function and then just switching the x and y coordinates. Then you can apply whatever transformations are required. And just as we saw the horizontal asymptote with an exponential function move vertically with a vertical shift, the vertical asymptote for a logarithmic function can move horizontally with a horizontal shift. So just as a quick example with this tabular method, if you had this function h of x is log to the base 3 of x plus 2, we have a vertical shift up 2 units. But I'm going to use its related function, the exponential function f of x is 3 to the x, to come up with the initial table coordinates, and then switch the x and y values to come up with the table of coordinates for the log to base 3 of x function. Then, once I have this table of coordinates, I can add 2 to the y coordinates to come up with the final coordinates that I could plot. Now, do pencil problem 5.